Welcome to the deep dive. We're going to be looking at, well, some really interesting science that came out in 2025, and we're going to be exploring this through a pretty intriguing lens.
Right.
Forget, thinking about the universe as like a collection of static objects.
Mm-hmm.
What if, it's fundamentally a grand interconnected dance of motion? You know what I'm saying?
Totally. This year's given us 5 fascinating scientific discoveries. And each one's a piece of a larger puzzle,
Yeah.
And our goal in this deep dive is to not just understand these findings individually,
Right.
but to actually connect them using something called motion theory. Think of motion theory as this idea that the basic building blocks of reality aren't still particles or like separate forces, but they're actually dynamic patterns of movement.
Okay.
And these patterns, interacting at all scales, create everything that we observe.
Right.
So we want to give you a clear and connected understanding of these cutting-edge ideas.
So motion theory says it's all about the motion and the patterns it creates.
Yeah.
It's a way to see the underlying unity in what looks like just a bunch of different stuff happening.
Absolutely.
All right, let's jump right into our first mind bender here. Something that's got cosmologists rethinking some fundamental assumptions.
Yeah. So this first discovery, for quite some time, the standard picture has been that the universe
Right.
isn't just expanding, it's
Right.
accelerating.
Yeah.
Like someone's constantly hitting the gas pedal.
Mm.
And the driver of this acceleration was thought to be this mysterious dark energy.
Right.
This force that's pushing everything further apart faster and faster.
Right, this invisible force making the cosmos just speed up.
Exactly.
But then the DESI telescope came along with its measurements, and what they're suggesting is it's pretty surprising.
It is.
It looks like this cosmic acceleration might not be constant after all.
Yeah.
The data indicates that the push from dark energy could be weakening. The universe is still getting bigger.
Right.
But the rate at which it's speeding up seems to be slowing down.
Yeah, what's particularly interesting here is how motion theory interprets this. Instead of invoking this separate enigmatic energy,
Right.
motion theory says that what we're observing as dark energy is actually the universe's overall pattern of motion, just naturally seeking equilibrium.
Okay.
Imagine like a complex fluid that's been stirred up.
Right.
It'll eventually settle back into a more balanced state.
Right.
So the weakening acceleration that we're seeing isn't some force fading away.
Right.
It's the universe's fundamental motion redistributing itself on a massive scale,
Okay.
moving towards a new dynamic balance.
So if I'm getting this right, instead of a spooky unknown force,
Yeah,
we might be seeing a natural shift in the universe's fundamental motion.
exactly.
It's like, the cosmic dance is changing its tempo a little bit.
I like that.
Does motion theory offer any insights
Yeah.
into whether, this rebalancing is a one-time event or perhaps, a cyclical process?
Right.
And what are the long-term implications for the universe's expansion if dark energy continues to weaken?
Yeah, that's a crucial question. Within the motion theory framework, this rebalancing isn't necessarily a final state.
Right.
Motion at this cosmic scale could involve, very long cycles
Okay.
of expansion and contraction, or perhaps shifts
Okay.
in the dominant patterns of movement.
Gotcha.
So the weakening acceleration might suggest we're entering a phase
Okay.
where the outward motion
Okay.
is becoming less dominant as other large-scale motion patterns begin to assert themselves.
Oh,
It certainly prompts us to kind of reevaluate the ultimate fate of the universe.
that is a huge shift in perspective for sure.
It is.
Okay, what's the next cosmic surprise on our list here?
Our second discovery comes from the incredible James Webb Space Telescope.
Okay.
And it's another one that makes you tilt your head and wonder.
Right.
Astronomers have been observing a large number of galaxies, and they've noticed this rather unexpected tendency.
Okay.
A surprising number of these vast collections of stars, gas, and dust
Right.
appear to be rotating in the same direction.
Wow. You just assume they'd be spinning every which way, completely independent of each other.
Inevitably.
Like a bunch of pinwheels just tossed in the wind,
I joke.
But this suggests that there might be a common spin,
Yeah.
a kind of coordinated motion across large swaths of the cosmos.
Exactly.
It's like finding out that all the merry-go-rounds in different amusement parks are turning clockwise.
Exactly. And if we consider this through the lens of motion theory,
Right.
it starts to paint a very different picture of the universe.
Okay.
Motion theory suggests that galaxies aren't isolated islands in space,
Right.
but rather they themselves are massive, structured patterns of motion
Okay.
within the universe's overall flow.
Okay.
Think of them as like giant whirlpools and a cosmic ocean,
Right,
as you
yes.
put it. A shared direction of rotation isn't likely to be just a random coincidence.
Right.
It strongly implies the existence of even larger
Okay.
underlying motion structures within the universe
Yeah.
that are influencing the spin of these galaxies.
So the key takeaway for me here is that we might be part of a much more interconnected cosmic structure than we realized.
Absolutely.
It's not just a random scattering of galaxies.
Yeah.
There seems to be an inherent organization, a kind of cosmic choreography
I like that.
happening on the grandest scale. How might these large-scale motion patterns have originated in the early universe according to motion theory?
Motion theory would suggest that even in the very early universe,
Okay.
there were inherent fluctuations and patterns of motion.
Okay.
And these initial motions,
Right.
through complex interactions and amplifications over vast periods of time,
Gotcha.
could have given rise to these large-scale structures and their associated rotations.
Okay.
It's like a ripple in a pond, creating larger and larger waves. The uniformity in spin direction could be a relic of these primordial motion patterns.
That's fascinating. Now let's zoom way down from these galactic scales to the incredibly tiny realm of quantum physics for our next discovery.
Absolutely. Our third finding takes us to the quantum level,
Okay.
where researchers at Brown University have made a very intriguing observation.
Okay.
They've detected something called fractional excitons.
Okay.
And what's particularly unusual about them is that they seem to exhibit fractional electric charges.
Fractional charges. That sounds like something you'd hear about in, theoretical physics, not something you'd actually observe.
Exactly.
Can you break that down a bit for us?
Yeah, so traditionally we understand electric charge as coming in, fundamental indivisible units,
Right.
like the charge of a single electron.
Right.
These fractional excitons, however, appear to carry charges that are fractions of this fundamental unit,
Okay.
like 1/3 or 2/3 of an electron's charge.
Got it.
This is quite unexpected, and it's generated a lot of excitement.
Yeah.
Because it could point towards new kinds of fundamental particles
Right.
or novel ways that charge can manifest at the quantum level.
Okay. My understanding of, basic physics is definitely being stretched here.
Sure.
How does motion theory make sense of these fractional charge carriers?
This raises a fundamental question.
Right.
Are these truly new fundamental entities with fractional charge?
Right.
Or is there another explanation?
Right.
Motion theory offers an alternative perspective.
Okay.
It proposes that what we're observing aren't new fundamental particles,
Okay.
but rather they're these complex synchronization patterns
Okay.
of those underlying structured motion loops happening at incredibly small scales.
Right.
Remember, motion theory posits that what we perceive as particles,
Okay.
including electrons and their charge,
Right.
are actually stable, repeating patterns of motion.
Okay.
So fractional excitons, in this view, could be specific temporary configurations
Okay.
where these fundamental motion loops are interacting and synchronizing in a way
Right.
that manifests as a fractional charge when we measure them.
So it's not that the fundamental unit of motion is being divided, but that its effects are being observed through these more intricate interactions.
Exactly. It's about how they're interacting and the patterns that emerge from that.
Does this perspective offer any testable predictions?
Oh, yeah, absolutely.
That could differentiate it from the standard model's interpretation of new particles?
Absolutely. Motion theory might predict that these fractional charges are not carried by truly independent, stable entities in the same way that electrons are. Instead, they might always appear as collective excitations or specific patterns within a larger system of interacting motion loops.
Okay.
So experiments designed to isolate and manipulate these fractional charges might reveal behaviors that are more consistent with transient patterns of motion rather than stable individual particles.
Okay.
Does that make sense?
That's a really different way of thinking about it.
Yeah.
All right, let's move on to our fourth discovery, which again involves the behavior of electrons, but in a very different context.
Indeed. Researchers at MIT
Okay.
made a surprising observation.
Okay.
They found that electrons,
Right.
which we typically imagine as these rapidly moving,
Right.
almost chaotic entities buzzing around atoms,
Yeah.
can actually arrange themselves into orderly,
Okay.
crystalline structures when confined to extremely thin materials.
Electrons forming crystals. That's like seeing a swarm of bees suddenly arrange themselves into a perfect honeycomb. You know what I mean?
Right.
It goes against our usual picture of these tiny energetic particles.
Yeah.
What's the conventional scientific explanation for this unexpected organization?
The standard understanding is that, this is quite remarkable because electrons, being negatively charged,
Right.
naturally repel each other.
Right.
Their tendency is to spread out
Yeah.
and maintain distance.
Right.
So to observe them spontaneously forming these stable geometric lattices
Yeah.
suggests that in these extremely confined environments,
Yeah.
some other forces or energy minimization principles are at play,
Right.
overcoming their mutual repulsion and driving them into these ordered arrangements.
Okay, so what's the motion theory take on these electron crystals?
If we look at this through the lens of motion theory,
Yeah.
we return to the idea that electrons are not just point-like particles,
Right.
but they are in fact loops of structured motion-seeking states of stability
Right.
and minimum energy.
Okay.
When these electrons are confined to incredibly thin materials,
Okay.
their possibilities for chaotic, random movement are significantly restricted.
Right.
So in this constrained environment, the most stable and energy-efficient way for these motion loops to interact might be to organize themselves into these ordered crystalline patterns.
Oh.
Instead of bouncing around randomly and repelling each other,
Right.
they find a configuration of movement that minimizes overall energy
Right.
within the given constraints.
Okay.
It's not a change in the fundamental nature of the electron,
Okay.
but rather the inherent tendency of structured motion to find the most stable arrangement under specific conditions.
So the key insight here is that order can emerge
Yes.
not from some external organizing force acting on the electrons,
Yeah.
but from the internal dynamics of their structured motion, optimizing itself within the given constraints of the thin material.
Yeah.
It's like the electrons, when their chaotic dance floor shrinks,
Yeah.
they naturally find a more synchronized and stable routine.
Precisely. And our final discovery
Okay.
takes us back out to the vastness of space.
Okay.
But this time, focusing on a very elusive messenger.
Right.
Scientists, using a neutrino telescope deep in the Mediterranean Sea, had detected a super high-energy neutrino that originated from far beyond our own galaxy.
A ghost particle from the depths of the cosmos.
Yeah.
Neutrinos have always seemed incredibly mysterious,
They are.
because they interact so rarely with anything.
Yeah.
Why is detecting one with such extreme energy so significant?
Neutrinos earned their ghost particle nickname because they interact with matter
Right.
through only the weak nuclear force and gravity,
Right.
which are incredibly weak forces at these scales.
Right.
This means they can travel through vast amounts of matter,
Yeah.
like entire planets,
Yeah.
with very little chance of colliding with anything.
Yeah.
So detecting any neutrino is a challenge,
Right.
but to detect one with such exceptionally high energy
Right.
coming from outside our galaxy
Yeah.
is a rare and valuable event.
Yeah.
It provides us with the direct probe of some of the most energetic and violent phenomena occurring in the distant universe,
Wow.
as these particles can travel unimpeded across cosmic distances.
Right. So it's like receiving a very faint signal
Yeah,
from a very powerful event light years away.
absolutely.
Now, how does motion theory interpret these ghostly,
Yeah.
high-energy travelers?
From a motion theory perspective, these neutrinos, even these high-energy ones,
Right.
aren't fundamentally different in kind from other forms of,
Okay.
matter or energy.
Okay.
They're also structured motion loops,
Right.
but likely oscillating at extremely high frequencies.
Okay.
The reason they interact so weakly with ordinary matter,
Yeah.
why they are so difficult to detect,
Right.
could be because these very high-frequency motion loops rarely resonate or synchronize
Okay.
with the lower frequency motion structures that make up our detectors and the ordinary matter around us.
Gotcha.
However, when a very high-energy neutrino does interact,
Right.
it signifies a brief but energetic synchronization
Yeah.
between these disparate frequencies, allowing us to detect it.
Okay.
This detection shows us that motion structures at incredibly high frequencies and energies
Wow.
are propagating across the cosmos,
Yeah.
carrying information about extreme events.
So the key takeaway here is that even these seemingly elusive ghost particles
Yeah.
can be understood within the framework of motion.
Absolutely.
They're not some fundamentally different type of entity,
Right.
but rather they're just different patterns and scales of motion,
Exactly.
operating at frequencies that make them largely invisible to us.
Mm-hmm.
Their rare interactions offer a glimpse into the wide spectrum of motion happening throughout the universe.
So to quickly summarize, we've explored how the potential weakening of dark energy could be the universe's motion rebalancing.
Right.
The correlated rotation of galaxies suggests large-scale underlying motion patterns.
Right.
Fractional excitons might be novel synchronization patterns of fundamental motion loops.
Right.
Electrons forming crystals demonstrate how structured motion optimizes under constraints. And even high-energy neutrinos can be seen as high-frequency motion loops, traversing the cosmos.
And our goal today was to help you, our listener, not just hear about these exciting scientific discoveries from 2025, but to see how they might be interconnected through this fascinating idea of motion theory.
Absolutely.
Hopefully you're starting to see how thinking in terms of motion and its patterns could provide a new and unified way of understanding reality.
This raises a really interesting question.
Okay.
For you to ponder.
Great.
If everything we observe, from the smallest quantum phenomena to the expansion of the entire universe, can be viewed through this lens of motion and its intricate patterns, where else might this framework offer valuable insights?
Right.
Could motion theory potentially shed light on other complex scientific challenges?
Right.
Or even help us understand patterns in seemingly unrelated fields?
That's a great question.
What other seemingly disparate phenomena in the world around us might be connected through this fundamental language of motion? It's a perspective that invites a lot of further thought and exploration.
Absolutely. It definitely leaves you with a sense that there's a deeper level of interconnectedness to everything than we might ordinarily perceive. Thanks for taking this deep dive with us.
It was a pleasure.
We encourage you to keep considering these ideas and see where the concept of motion might lead your own understanding of the universe.
Absolutely.
Thanks for joining us.
It was great being here.